importante, né?
Já tá gravando. Vai lá.
Good morning, my name is Danusa. I'm a postdoc in the Department of Biochemistry here at UFSC. Thank you for this opportunity today to give a talk here in the Department of Physiology. Today I will be talking about two different techniques, patch clamp and calcium imaging. And these techniques are very important to study the new therapeutical targets through electricity, the measurement of electricity. And I will start talking about patch clamp with some data that I have acquired in the last years. And in the end of the presentation, I'm going to speak about calcium imaging, showing one more time the data that I have acquired in the last years. So first of all, a little bit of history from electrophysiology to patch clamp. The discoveries in the field of electrophysiology, they are found every 100 years. And it was in 1952 that Hodgkin and Huxley, they found out the intracellular recording, the mathematical model of an action potential, and received the Nobel Prize for that in 1963. The patch clamp was discovered in 1976 by these two researchers here, Neher and Sackman. They found how to measure the voltage of the cells and found the recordings of single channels, and they received the Nobel Prize in 1991. So it's very important to understand this figure here. This figure shows a cell, a single cell, in a basal situation. This is a cell with the resting membrane potential negative, which ensembles all the cells in our body while they are in basal conditions without any kind of stimulus. So here we have a basal situation where we have a negative membrane potential inside of the cell. And the figure also shows that we have high amounts of potassium inside of the cell and high amounts of sodium chloride and calcium outside of the cell. This figure is important because in the technique of patch clamp, we have a software connected to our cells, which it's an amplifier of signals. This amplifier, it's going to give to the cells different kind of pulses. And through these pulses that the software is going to give to the cells, we are able to study different kind of channels. For example, if you want to study potassium channels are activated in depolarizing potentials. So we are going to give a protocol for our software, and then our software is going to give a pulse to our cells, a depolarizing pulse, and then we are going to be able to study the potassium channels. If you want to study sodium and calcium channels, for example, we are going to give a protocol for our software where it's going to give a hyperpolarizing potential to the cells, and then we're going to be able to measure sodium and calcium channels. So in the basic situations, what you have is high amounts of potassium inside of the cell. So whenever you have a depolarizing effect, for example, in the action potential, first we have either the influx of sodium or calcium to inside of the cell. This effect to happen, we need to give a pulse to the cell to be activated. Whenever you have a very positive potentials inside of the cell, we are going to have the efflux of potassium, which it's going to be the action potential. So knowing this figure very well, it's easier to understand how patch clamp works, because patch clamp is connected to an amplifier, and this amplifier is going to give different pulses to study different kind of channels. That's the channels of interest of the investigator. So here I brought some examples. For example, what patch clamp does? Patch clamp can do two things. Either give a clamp for the voltage or give a clamp for the current. If you clamp the voltage, we're going to study the currents that goes through the cells. And if you give a clamp for the current, we are going to study the voltage that goes through the cells. So this is two different things. When you give the voltage clamp through our amplifier, which is our software, we're going to study the chloride and potassium currents that goes through these channels. For example, here I gave a depolarizing potential, very high depolarizing potential. You can see the efflux of potassium or the influx of chloride in the cells. That's the way it's done. We give depolarizing steps from -6 to 60, and we're going to have the potentiation of potassium and chloride channels in this voltage. If you want to study sodium and calcium channels, you are going to give negative hyperpolarizing potentials to this cell, and then this is the pulse from -100 to -20, and then you are going to be able to study sodium calcium currents that go through these channels. So this is for voltage clamp experiments. When you do voltage clamp, you fix a voltage and you study the current. When you give a current clamp, you fix the current and then you study the voltage. The voltage, here I have an example. I gave a dose response curve for KCl, and you can see a dose response curve of the voltage, the membrane voltage changing from the resting membrane potential of the cells according to the concentrations of potassium. And here you can see that action potentials, they are measured when you have a current clamp. You can fix the current -50 millivolts, and then you are able to measure action potentials, spontaneous action potentials coming from the cells. So in this figure is just to make clear that patch clamp, it's very interesting because patch clamp can study only one single cell in the system, only one single cell, and you have choices. You can either study one single channel in this unique cell, or you can study the whole cell. That means that you have the access to the whole cell, and then you study all the channels that are localized in the plasma membrane of the cells. So we have to understand that patch clamp can only measure the flux of ions that goes through the plasma membrane of the cells. It's not capable to measure plasma membrane of nucleus or organelles or nothing like that. It's just possible to measure the currents that go through the proteins that are localized in the plasma membrane. So here we have sodium, calcium, potassium, chloride channels, which are the most studied channels through patch clamp, but you can also study channels that are activated by neurotransmitters or that are activated by intracellular ions or nucleotides, and also you can study the pumps. You can study sodium potassium pump, calcium pumps, or other kinds of pumps. There are many diseases that are involved in the study of ion channels. For example, the most studied diseases are in the field of neuroscience. You can measure, you can study depression, anxiety, schizophrenia, epilepsy, pain, memory, but you can also study other kinds of diseases. For example, in our lab, we are studying diabetes, we are studying cancer in collaboration with other labs, and also we are studying infertility. How these channels are involved in the pathophysiological functions of these diseases in the presence of different kind of analogs. And here I like very much this example because here you have a normal neuronal action potential firing. So this would be in the normal basal situation. You have action potential firing, and here you have two different situations. For example, here you have a hyperexcitability of action potentials. There is an increase in the frequency of action potential firing. And in this case, we have a lot of pathologies involved with this case. For example, seizures, pain, anxiety, bipolar disease. This can be found in patients with this kind of disease. So this is only to show you that if you add to the system or if you manipulate these potassium channels with some activator of potassium channels, what's going to happen? Potassium channels is going to leave the cell, is going to happen the efflux of potassium from these cells, and then the cells are going to go back to the normal neuronal action potential. If you manipulate these potassium channels here, to show you how important it is to study patch clamp, because patch clamp is the main technique that you can study directly the flux of ions that goes through the potassium channels, for example. And here you have another situation. You have the decrease of frequency of the action potentials firing, and this is what happens when people have depression, disorders like multiple sclerosis or cognition disorders. So this is very interesting because in this case you do not use a channel activator of potassium, but you would use an inhibitor of potassium channels. So potassium would keep inside of the cell, and then the cell would go back to firing the neuronal action potential. So this is only an example to show how you can interfere with drugs through these channels to keep the brain in the basal condition of normal firing. These drugs are used to treat all these kind of diseases together with another kind of drugs. So there are different kinds of patch clamp configurations. Here you can see a single cell. So we are going to go closer to the cell, and then you are going to have a different resistance whenever you touch the cell. When you touch the cell, you have the chance to find a single channel in the plasma membrane to study single channels. It calls the cell attached configuration. Here we measure this channel in the lab. It's a single channel here. It's opening and close, opening and close, opening and close. But what you use the most in our lab is the whole cell. The whole cell, it's when you have the access to the whole cell. You have the access to all the channels in the plasma membrane of the single cell. So this kind of currents you can see here, this is a potassium currents that you can prepare a protocol for studying potassium currents. You prepare the solutions for studying potassium currents, and also you can block the potassium currents in the end of the experiment to show that was really a potassium currents. So now I'm going to show you some experiments that you have done in the lab. But first of all, you have to prepare some solutions to study patch clamp. You have to prepare physiological solutions that mimetize our organisms. For example, like I said, in the intracellular media we have high concentrations of potassium, and in the extracellular medium you have high concentrations of sodium, chloride and calcium. So all the solutions you make in the lab, they are just the same thing that happens in vivo. So first of all we prepare the solutions, and then with all the equipment you have available in the lab, you can measure the voltage and the currents that goes through the cells. So here is just to show you very quick that how we do that with the help of the software. So first you measure the resistance of the pipette, which should be 4 megaohms. Then you touch the cell with the pipette, and you can see the resistance that goes up because the seal that's made between the cell and the pipette are very high resistance. So we are going to see this seal, this resistance going up to 1 gigaohms or more. And here in this configuration you're already able to measure the single channels of the cells. But then you need to do an extra suction to have finally the whole cell configuration to measure the currents that go through the channels. This is a very difficult technique. You need a lot of patience to be succeeding this technique, and it's very important to have a very viable cells, so the cells are going to respond easier for your resistance. And another thing that's very important is the solutions. They should have the pH very around 7.4, and the osmolarity should be between 290 and 310. So we can measure all this through the equipment in the lab, but this is the most important thing. The cells should be viable and the solutions should be perfect. So here I have more examples to show you that you have done in the lab. We had a collaboration with another lab where we acquired the mesenchymal stem cells from human placenta. It's a collaboration where I took the cells just to set up the equipment. I had the equipment, but at that time I didn't really have the cells, so I needed to set up the equipment. I took the cells from my neighbors, and I was able to measure the polarization of the cells in the presence of different kinds of concentrations of KCl. And also I was in the current clamp configuration, I was able to measure the action potentials that was very spontaneous. I didn't give any kind of stimulus, and these cells already were spontaneously triggering the action potentials. What was very interesting, because